Hello, today I will tell you what is dimensionality reduction methods and why do we need them. So essentially, dimensionality reduction is a process of decreasing number of features in your data from m to k, where k is less than m. And there are various reasons why do we need such methods, and we will start with a relatively simple example which illustrates one of these reasons. So imagine you have a spring attached to a wall, and you pull this string up to some point, this red point right here, and then you release this spring and you record the x and y position. So this is the x-axis and this is the y-axis. You record x and y position of the end of the spring as you release it. So essentially this process is one-dimensional, right? The only direction which changes is the x. We also have a small deviation for the y-axis, but it's mostly just a noise. But now imagine we don't have access to these measurements. What we do have instead are the measurements from three cameras: camera A, camera B, and camera C. And these cameras, they recorded the whole procedure from their positions. So they record the x and y position of the end of the spring in some plane, and this plane like unique for every camera. These planes will differ from the xy plane because these cameras, they are under some angle and they're under different heights, so the planes will be different, but the time component is the same. So for every moment in time, we have x and y position of end of a spring on a camera A, x and y on a camera B, x and y on a camera C. And these are those observations. So essentially we have described one-dimensional data by a six-dimensional vector, right? And this is kind of bad. This redundancy is bad. You need to keep track of like 6 features instead of like 1 or 2. So what could we try to do with that? We could try to reduce the dimensionality of the data from 6 to something smaller. Okay, I've already created some simulated data. So this is the original data of like changing the x position of the spring as you release it, and this is a small noise along the y-axis, and this is the data from camera A, B, and C. So what we want to do, we want to somehow reduce the dimensionality from 6 to 1 or maybe to 2. And we will use, so this is the our six-dimensional data. And we will use a PCA, principal component analysis, for that. So the PCA is a linear method of dimensionality reduction. What do I mean by linear? I mean that this procedure of going from an X matrix of size n by m to the reduced X matrix of size n by k is via matrix multiplication. So basically how PCA works, it multiplies your original matrix by some rectangular matrix of size n by k, and you end up with a matrix X reduced of a size n by k. The tricky question is how do you obtain this matrix S, but again we will not go into that part, the implementation part of the PCA. If you really want to know that, you could go to this PCA tutorial, a great paper. I highly recommend to read it. So this example is taken from there. Okay, so we somehow compute this matrix S, and then we multiply our original matrix X by S, and we get our reduced representation of the data. Let's see how it works on practice using an sklearn implementation. So the PCA is taken from the decomposition submodule, and it really have a single important parameter and components, and components is a parameter controlling number of so basically n components is a k. So let's plot this data. this is the data after the decomposition, after we apply the PCA method to them. So we could see that we really got a beautiful, almost one-dimensional with small deviation over the second dimension, the data. So the PCA gives us so-called variance of the components. So the PCA components, since this is a linear method, PCA components are a linear combination of the original features. So you take your original features, then you somehow rotate them, you sum them up with some linear, some numbers, and you end up with a PCA components. And the number of components in this particular case is equal to 2, and the importance, the importance of these components, in a sense that, like, how is this how informative is that component, is indicated by an explained variance, or by an explained variance ratio. So basically, explained variance ratio is the total variance, component variance divided by sum of the variances of all components. And in this particular case, we could see that the explained variance ratio for the very first component of the data is almost 1. So the total sum should be 1 over all 6 components. And you could see that the explained variance ratio of the first component is 0.97, of the second is like 2.7%, and then all the remaining components gives us no additional information. So what it tells us, that essentially this 6-dimensional data which we pass into the PCA is actually a 2-dimensional data and no more. And if we watch the elements of the first component, so basically this component with index 0 is the first column of the matrix S. We could see the weights of the original features. So as I told you, the PCA is a linear method, so every single principal component is a linear combination of the original features, and this is the weights in this linear sum. Okay, so let's move on. The second example is the example with MNIST. Quick reminder, these digits are simply handwritten digits which were translated into 8x8 pictures, and these images, 8x8 images, were reshaped into 64-dimensional vectors. So what we have here, we have X contains the pixel intensities, and Y contains the target variable, so either 0 or 1. And we could import like up to 10 classes, right? But for now, we only import 2 classes, 0 and 1. So let's plot. So instead of plotting a single number, let's plot first several observations, and we will use it using, again, an imshow. So let's plot first 10 rows of matrix X. This is like 10 observations. Every single row is a single observation. And what you could notice, like from the first glance, is that some of the columns of this matrix are blunt. They are completely 0 everywhere for every single observation. What it means? It means that these columns are completely redundant. They are constant for all observations, therefore they don't contain any important information. They always 0, right? So what we could do, we could try to reduce the dimensionality of this data. So maybe instead of 64 features, we will have, I don't know, maybe 30 features or 20 features or something like that. Okay, but we don't know on the beforehand how much. So let's start with a PCA and let's use 64 components. So we will end up with a explained variance ratio for 64 components, and then we will choose number of components which will sum up to some like huge ratio, like 0.9, for example, 0. I don't know, 8. So let's see the explained ratio. This is explained ratio of the individual components. If we compute a cumulative sum, we will see that, let's say, first 1, 2, 3, 4, 5, 6. First 7 components already explains like 80% of the variance in the data. And first, let's say, 8, 9, 10, 11. First 12 components explains like 90% of the variance of the data. And I don't know what number is it, so somewhere about 25 components basically explains all the variance in the data, and all the remaining components are just redundant, completely redundant. So what we could do now, we could project our data only on the 2 first components, on these 2 components, and plot them as a scatter plot, right? So what we have now, what we have here is a plot of the features of all observations, but now we could project this data onto 2-dimensional plane and plot it as a scatter plot. So on this scatter plot, let me actually remove the color, so it's like already a spoiler, but whatever. So every single point on this plot corresponds to a single observation in the original X, right, in the original data. And you already know that the, so basically these black points here are like 1s, and these yellow points here are 0s. So we could see that once we project them into a 2-dimensional plane, the plane of the first and the second principal components, we could easily differentiate them. We could actually easily differentiate them even in this like 64 dimensions, but here we could like visualize them. So what we could do, we could visualize, now we could visualize this data. Once this data was in 64 dimensions, we could not visualize them. And once we project them into a 2-dimensional plane, we could like get a beautiful picture. Additionally, what could we do? Let's say we could sample a point somewhere from this region, right, in these 2 dimensions, and then apply an inverse transformation. So the transformation that transforms, so basically what we do, we sample a point and then we multiply this point by S inverse, right? And what we got, we go from reduced space to the original space. And let's see the results. So I took a random point from this point cloud. So this is minus 20, 0, minus 20, 0, somewhere from here. And then I apply an inverse transformation to that. And then I reshape the 64 long vector into 8 by 8 picture, and I plot this picture. And what I got a nice and pretty like realistically looking 0. I could do the same thing with like these yellow points here. I could sample some points somewhere from this yellow cloud and get like kind of the same result. So this is a nice visualization, nicely handwritten one, right? So we could actually sample data from the PCA distribution and then apply an inverse transformation and get realistic visualization of this data. So get realistic object in the original space. And obviously, if you try to sample the data from the original space, so first of all, it's computationally like insanely hard to sample the data from the multidimensional, like some complicated multidimensional distribution. So typically what we do instead, we sample like uniform distribution, or maybe from a Gaussian distribution. So let's try to sample some point from a uniform distribution in a 64 dimensions, and then reshape it into 8 by 8 picture and plot it. So obviously we got nothing to do with either 0, 1, or any other digits. Okay, so things went pretty with 2 digits like 0 and 1. Let's say we increase number of digits to 5. What's then? Right? I don't know, maybe this one. So this is probably 4. No, okay, it's 1. Maybe this one. Again, so it's all ones. So let me see. Am I okay? I'm insanely unlucky. I don't know, maybe 62. So this is probably 4, and maybe 79. This is probably also 4. Maybe we should take 0, 1, 2, 3, 3. So this is 3 and this is 4. Okay, let's try to run PCA again. So you could see that the explain ratio changed because we actually changed the original data set. So we changed the x, right? So x now is not only 0 and 1s, but also 2s, 3s, and 4s. And we run PCA again. So the whole transformation, this matrix computed by a PCA changed, and the explained variance ratio also changed. So now we need more components to explain like 80% of the data, 90% of it. So if we now try to project the whole data onto two-dimensional plot, we will not get this very beautiful picture. The picture will be like more messy. So if I remove the color, it's not that obvious which number are what. Okay, so we do have some clusters of numbers, clusters of points here, but it's not that obvious as it was with when we only have a 0 and 1. Okay, so this method is not and actually like there are no silver bullet method which will reduce the dimensionality of your data to the 2 dimensions and not waste and not lose any information. Okay. Okay, so let's move to the next example. So basically the next example is a method called TSNE. TSNE is a very powerful method of a dimensionality reduction. So it's not a linear method as it like PCA, but it's a highly nonlinear method, which again allows you to reduce the dimensionality of the data. The like bad thing with the TSNE is that it's not a deterministic method. So if I ran this method once again with a different random state, I will get a different representation of a low dimensional data. Okay, so obtained representation is different. And there are many different parameters of TSNE, like the perplexity, learning rate, number of iterations. So it's an iterative method. It's a highly complicated method, but it's a very powerful one. So sometimes if you want to get a nice 2-dimensional representation of your data, for example, for visualization purposes, TSNE is a very nice method. It's not that easy to cook it, but if you learn how to do that, you will end up with a very pretty 2-dimensional pictures. Okay, so let's see how it works on the real data. Let's actually load our data from the previous seminar. And let's try to project this data onto 5 dimensions. So we will only take numerical features from our data set. So it will be number of unique departments, number of unique find lines, number of unique scan counts, total number of scan counts, and total return. And we will project them, so there are a total of 5 of them. We will train a PCA with 5 components, and then we will see the explained variance ratio, and based on the value of explained variance ratio, we will select the number of components. So let's run the method, and what could we see? We could see that actually a single component, single PCA component explains like 96% of the variance of the data. So basically what it means that we could remove all these 5 features and we could replace them with a single feature, which is a linear combination of them. Okay, so what kind of linear combination? Basically this is the answer. So you should take 16% of unique department, you should take 47% of a unique find line, so on and so forth. So basically you take a column unique department, you multiply it by 0.16, then you add up with a unique find line multiplied by 0.47, then you add to the sum number of unique scan count multiplied by 0.55, and you add up like a total scan count multiplied by 0.66 and the total return multiplied by like 5 over 10,000, right? And you end up with a single feature, which is a combination of the 5 original, but originally you have 5 of them, and now you only have a single feature. So we could compare this result with the feature importance, which we got again in a previous seminar using CatBoost, and we could see that actually some of these numbers quite nicely coincide. So for example, this is the highest coordinate of the first principal component, and it corresponds to the feature total scan count. And total scan count is like the highest ranking numerical feature in the feature importance according to a CatBoost, right? So we also have a unique find line and unique scan count, which are somewhere here. So basically they are not that important according to the feature importance of a CatBoost. But maybe if instead of a unique like total scan count, we have used the first principal component computed on these 5 features, maybe our CatBoost performance would be better. So this is not usually a very effective idea to reduce the dimensionality using a PCA or a TSNE for like using the resulting features in a some classification or regression problem, but it is viable. So sometimes it might work, and you could actually test it whether it will work in this particular case or not. Okay, so let's conclude. Why do we need the dimensionality reduction methods? So I would say these are the most popular reasons. So first, you want some methods to reduce the noise in your data. If you have a very noisy data, then maybe reducing dimensionality should help, right? Second is the visualization purposes. So visualization purposes is really a very important part, very important reason for these methods to exist. And finally, for data sampling, and typically like there are some real world examples where kind of like very simple dimensionality reduction model allows you to very effectively reduce the number of dimensions and then sample a point in this small dimension and then apply an inverse transformation and got a point, like realistic point in the original space, apart from this MNIST example. But again, they are kind of rare. So there are many different dimensionality reduction methods apart from PCA and TSNE. There are like several dozens or maybe even hundreds of them, and they all differs by an like internal idea of how do you go from M features to K features, right? It could be a linear method like a PCA where you have like different approaches of computing this S. So this S could vary. For PCA, it's one S. For, let's say, LDA, it's another. For something else, it's the third one. It could be a highly nonlinear, like TSNE, like iterative method. But and in some cases, one method will work. In other cases, other methods will work. But essentially, all these methods, all what they do, they decrease the number of features from like large number to a smaller number somehow. Okay, so this is it for this seminar, and I see you on Thursday. Bye.